All right. Good evening, everyone. So I'll record lecture 19 here, and this is going to involve finishing up the chapter on stereochemistry, and then we'll start chapter 7 on cycloalkanes. Okay. So there are two more points that we need to cover before we finish our discussion of stereochemistry. And so the first are what we call diastereomers. Okay, and there's a very simple definition for diastereomers that it's important to remember and not get confused. When you're thinking about this, diastereomers are simply stereoisomers that are not mirror images of each other. And so what do I mean by that? So let's consider a molecule with two stereocenters, for example, bromochloroethane, bromochlorobutane. Okay, so I intentionally drew that without any stereochemistry. We can start to draw the different stereoisomers that can exist for this molecule. And so how I draw the first one is going to be completely arbitrary. And I think what I'd like to do is put this methyl group in plane, put the bromine in plane, and then use my lines and wedges for the remaining substituents. So the methyl group on the right, I'm going to put coming out at us. And there's a hydrogen going back, so I didn't draw that in the first structure. It's implicit. And then I'll put the chlorine coming out. And the hydrogen is going back. So, okay. And so I can work out the absolute configuration of each center in this molecule. And so if I do it for the carbon on the left, this is priority 1, this is 2, 3, and 4. And then looking down the bond to the lowest priority substituent, I draw an arrow, and that arrow runs in a counterclockwise direction. And so that is the S configuration there. And if I do it on the other side, I have 1, 2, 3, 4. And now if I look down the carbon-hydrogen bond, the arrow runs in a clockwise direction, so that center is of the R configuration, okay? And so what I can then start to do is start to invert the two stereocenters, and we'll just do them one by one. And so first thing I'm going to do is invert the center on the right. And so I'll redraw the center on the left because that's not changing. Okay, and then I can invert the center on the right. The easiest way to do this is just to exchange two substituents. So I'll leave the methyl group where it is. And I'll swap the hydrogen and the chlorine. So now hydrogen's coming forward, chlorine's going back. And so the configuration on the left hasn't changed. This is still S. Okay, the one on the right now should be S, but why don't we take a moment to verify that? So this is chlorine is 1, this is 2, this is 3. Okay, and to see that it's S, I have to flip it over 180 degrees and look down the carbon-hydrogen bond. And when I do that, I can see that the arrow is running counterclockwise. Okay, and so this is the S configuration. All right, and so then I can return to the first structure and say, all right, let's invert the center on the left-hand side. So we'll start by drawing the right-hand side in identical configuration. And again, to do the inversion, I'm going to swap the substituents on the hash and the wedge. So I'll leave the bromine where it is. Now the hydrogen's coming forward, the methyl group's going back. Okay. Nothing has changed on the right side, so the configuration there is still R. Okay. And the configuration on the left should change from S to R, but again, we can work through that. 1, 2, 3, 4. And so I need to sort of flip the molecule over 180 degrees to look down the carbon hydrogen bond. And when I do that, I can see that the arrow runs in a clockwise direction. So that is in fact R. Okay. And then finally, we can flip both stereocenters. And so in the lower right, I can draw a fourth stereoisomer. Okay, so I flipped the one on the right to S, and then the one on the left, I'm going to change to R. And so that will be the same as what I've drawn immediately to the left of this one. So this is R. Okay. So these are the 4 possible stereoisomers of this molecule. In general, for a molecule with N stereocenters, you can have up to 2 to the N possible stereoisomers. Okay, you don't always wind up with 2 to the N possible isomers. In some cases, because of symmetry, you get less potential configurations than that. But that is the maximum number of possible stereoisomers. And so the question is then, what's the relationship between these 4 molecules? Okay, and it's important to remember that, you know, the enantiomer of R is S and vice versa. And so if I have a molecule that has 2 stereocenters and they're both of the R configuration, the enantiomer of that molecule is going to be the SS stereoisomer. And so in other words, these 2 molecules are enantiomers. Okay. In a similar fashion, if I have a molecule with SR configuration, the enantiomer of that is RS, and I can see that going from the top left to the bottom right. Okay, so I call that A as well. Okay, so the relationship between those 2 in the corner is that they are enantiomers. All right. Everything else are diastereomers of one another. Okay, so stereoisomers that are not mirror images. The mirror image of SS is RR. Anything else is a diastereomer. So the relationship between these two is that they are diastereomers. The relationship between the two on the top, they are also diastereomers. Okay, the two on the left-hand column and the two on the bottom are also pairs of diastereomers. Okay, so enantiomers have a very specific relationship. They're non-superimposable mirror images, and then diastereomers are everything else. Okay, relationship between all other stereoisomers. Okay, the other point that I want to make is that not to let the terminology confuse you. So the diastereomer may imply may imply two stereocenters. Okay, this logic applies to things with 3, 4, 5, 6 infinite number of stereocenters. We always introduce it concept with two stereocenters because that's the simplest case where we find diastereomers. But it doesn't. The term di doesn't refer to two in any way. It just means more than one. Okay. All right. So there's an important point, which is that while enantiomers have identical physical properties, diastereomers have different physical properties, and so they have different they can have different melting points, different boiling points, different spectroscopic properties. Essentially, every sort of feature of them can be different. In practice, these are often quite similar, but they are by definition allowed to be different, whereas enantiomers have to be identical. Okay. So that's all I really want to say for stereochemistry. Maybe we could just review a couple terms here before we conclude this chapter. So, in a very general sense, isomers are molecules that have the same chemical formula but different arrangement of atoms, right? Constitutional isomers differ in their connectivity. So examples would be N-butane and isobutane, okay? This chapter was not focused on constitutional isomers. Conformational isomers differ by facile bond rotation, okay? And so we saw examples of that when we talked about eclipsed and staggered conformations of ethane. Those are conformers, and they are conformational isomers of one another, okay? In this chapter, we talked about stereoisomers, which differ in the arrangement of atoms in space, and they can't be interconverted by any sort of facile process, okay? Chiral molecules are molecules that lack a plane or point of symmetry. They have a non-superimposable mirror image, which we call an enantiomer. They rotate plane polarized light, and the stereocenters in chiral molecules have an RRS configuration, okay? Enantiomers specifically are stereoisomers that are non-superimposable mirror images of each other. They have the same physical properties, save for the rotation of plane polarized light. Diastereomers are everything else. They are stereoisomers that are not mirror images of each other. And then mesocompounds are compounds that contain stereocenters, but overall have a plane or point of symmetry. And so the molecule itself is achiral, okay? And so this is the vocabulary of stereochemistry, and it's very important to become comfortable with these words. And so we distributed, courtesy of Wendy, that flow chart that outlined everything. I'd encourage you to take a look at that. There's a similar flow chart in figure 6.11 in your text that outlines these relationships. But these are terms that you want to have down cold, okay? All right, so that concludes the chapter on stereochemistry. The next chapter, chapter 7, is on cycloalkanes. And this is one of the most fun chapters in the book, because we're going to introduce concepts like ring strain, which relates to the sort of destabilization of molecules when you form rings, and we'll sort of unpack how those are, where that strain comes from. And we'll also talk about, we'll spend a lot of time talking about cyclohexanes, most common cycloalkane, and its various conformers, which has a quite rich sort of conformational landscape that's very interesting to talk about. So, all right, so the general formula for a cycloalkane is CnH2n, which is equal to N times the number of CH2 groups, okay? So, for example, if you think about the simplest cycloalkane, cyclopropane, the formula here is C3H6, and this is equal to 3 times CH2, okay? All right, so the way we're going to introduce this idea of ring strain through heats of formation by thinking about the heats of formation of cycloalkanes. And so let me just remind you that the standard heat of formation, delta HF naught, is equal to the heat that is evolved when a molecule is formed from its elements in their standard state. So okay. And so the sort of natural state of hydrogen is dihydrogen H2, carbon is graphite, oxygen is dioxygen O2. The more negative the delta HF naught, the more stable the molecule. Okay. And so we can, the heats of formation of simple cycloalkanes are well known, and we can make a small table here. So we'll just do cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane, okay? Oops, I'm getting cut off there. And the standard heats of formation are as follows. So these are all in kcals per mole. So cyclopropane is plus 12.7 and cyclobutane is plus 6.8. Okay, so in other words, those molecules are less stable than their elements in their standard state. I need to put heat in to actually make those. Okay. For cyclopentane, the heat of formation is minus 18.4. Cyclohexane is minus 26.5, or sorry, 29.5. And cycloheptane is minus 28.7. Okay. And so we can't really, you can't compare heats of formation between molecules that have different formulas. It's sort of it's apples and oranges. So in order to kind of compare the stabilities of these molecules, we're going to divide these heats of formation by the number of CH2 groups in the molecule. So we can make a second column with delta HF not over CH2, okay? And so here we're going to get plus 4.3 plus 1.7 minus 3.7 minus 4.9 and then minus 4.0, okay? And so this then allows us to have make a better sort of comparison of the relative stabilities of these molecules. And what we can see is that cyclohexane on a per CH2 basis is the most negative. So this is okay. So this is the most stable cycloalkane of the ones that I've drawn. Okay, and so we should keep this minus 4.9 kcals per mole in mind here for what I'm going to show you next. So what we're going to do next is look at the stabilities of the heats of formation of straight chain alkanes going from pentane to hexane to heptane, C5, C6, C7. Okay, so the heats of formation of these molecules are minus 35.0, minus 39.96, and minus 44.88. Okay, and if I look at the differences, the successive differences between each of those, I can get sort of a delta for each CH2 group. So the delta here is minus 4.96. The delta here is minus 4.92. So overall, for acyclic saturated hydrocarbons, I give off about 4.9 kcals of energy for each additional CH2 group. So And remember on the last slide that we said that each CH2 group in cyclohexane is worth about minus 4.9 kcals per mole. And so essentially cyclohexane is as stable as acyclic saturated alkanes, okay? And so what we say is that cyclohexane has no strain energy, okay? There's no energetic penalty for wrapping 6 carbons around into a ring. The delta HF naught per CH2 for cyclohexane is approximately equal to HF naught CH2 for straight chain alkanes. Okay, so so cyclohexane is our baseline. It has no strain energy. It's the most stable cycloalkane. So if you either go smaller or larger, you're going to start to introduce strain. Okay, and so this is a good point to pause the lecture. So I'll stop here, and then we'll do part 2 in a moment.